Oh, hi everyone. Welcome to our virtual pre-lab lecture. Our experiment this week is on chemical equilibrium, specifically determination of molar solubility of calcium iodide. By end of this lab, you should be able to determine the molar solubility of calcium iodide in pure H2O and in saturated calcium nitrate. Then from the molar solubility, you should be able to determine the KSP. Generally, molar solubility is defined as the amount of substance that can dissolve in a given amount of solvent. Generally, uh, the unit for molar solubility can be grams per liter or moles per liter, or basically just molarity. This is the units we'll be using, but some text have may use grams per liter for solubility. So the amount of solvent moles is always in liters. Now, you should be able to determine the molar solubility of a compound, and generally, the you will be given the KSP for an inorganic or ionic compound. Now, you should be able also to define the KSP, the equilibrium expression for a chemical dynamic chemical equilibrium. In this case, you should know the molar solubility in order to find the KSP depending on the ionic compound given. And lastly, uh, common ion effect. This is the tendency for a substance or for ionic compound to be less soluble in a solution with a common ion. These are the key terms you should know as far as this lab is concerned. Now, let's look at the background. In Gen Chem 1, you uh, you define or classified ionic compound as soluble or insoluble. However, those ionic compounds which are considered as insoluble have degree of solubility. And an example is lead to iodide, that it can, even though it is insoluble, it can cool into solution, and there is a dynamic equilibrium here from the expression between the dissolved ion in H2O. You read this as 1 mole of lead to produce 1 mole of lead 2 ion and 2 moles of H2O. If you look at the molar solubility, I mean the ion product constant, it is way too small because of the concentration of ion in the solution, which they exist in a dynamic equilibrium. This expression has 2 arrows pointing on either side for the fact that the dynamic equilibrium expression is going back and forth inside dynamic equilibrium. You can calculate the ion product constant, the KSP, given the solubility equilibrium. Today, this is the solubility equilibrium of calcium iodide. If you see the chemical formula for magnesium hydroxide, an example in the lab manual, for every 1 mole of magnesium that dissolve, there is 1 mole of magnesium ion and 2 moles of hydroxide ion. If you or we know the concentration of each ion, we can determine the KSP. Because of the small amount of small concentration of each ion, the ion product constant Ksp is way too small, 5 times 1 times 10 to negative 12 is the solubility product or Ksp. Uh, our solid or insoluble ionic compound, you will determine its Ksp is calcium oxalate, and the mole ratio here is 1 to 1 to 2. For every 1 mole of calcium iodide that dissolves, 1 mole of calcium is produced. From this slide, how you determine the molar solubility? You pick the ion whose ratio is 1 to 1 with the insoluble ionic compound. In this case, the molar solubility of magnesium hydroxide is based on magnesium because it's 1 to 1. For us, the molar solubility of calcium iodide will be a function of the molarity or concentration of calcium ion in the solution. So let's see how to determine the molar solubility. This depends on the ratio of ion. What I mean by ratio of ion, this is the ion in the solution. If it is 1 to 1, there's a way to determine the molar solubility. If it is 1 to 1, let's see, this is 2 to 1, this is 2 to 1. How do you determine the molar solubility? You say, let S be the molar solubility, and for 1 to 1, uh, is we have S as the molar solubility, and S times S gives us the ion product, and this is the equation to find the molar solubility given the Ksp. With that, it is just the square root of what? Square root of Ksp. This is for 1 to 1 mole ratio. However, for magnesium hydroxide, to get the molar solubility, it's slightly different for 1 or for 1 to 2 or 2 to 1, such as magnesium hydroxide or lead 2 chloride. How do we go about with that? For 2 to 1 or 1 to 2, if you know the Ksp and you're asked to find the molar solubility, it is just uh, 4 divided by, or Ksp, even the Ksp, square this 4 square, S is 2 or 4s squared times s squared, the 4 is 3, and the Ksp or solubility for 1 to 2, which is our iodide will work is also in 1 to 2. So we know the Ksp, you can determine the molar solubility from Ksp, or given the molar solubility, you can be asked to find the Ksp. For magnesium hydroxide, let's see, if you are asked to find the molar Ksp, you need to know the concentration of each ion. Look at the ratio. If you know the molarity of magnesium, we can use this relationship that twice the concentration of magnesium will be the concentration of hydroxide, or concentration of hydroxide. We know the concentration of hydroxide, we divide by 2 to get the concentration of magnesium. With this, we can plug in the equation to find the Ksp, to find the Ksp. Here is an example on the determination of the molar solubility of lead 2 bromide. lead to bromide given the KSP value. You plug in the equation to get the molar solubility based on the equation given here. The cube root is the same as raising the whole setup by 1/3. Please pay attention to significant figures. This is more than what we need. We have here three significant figures. This will be three significant figures. This is the molar solubility of lead to bromide in pure H2O. If it was just a 1-to-1 ratio, we just take the square root of the KSP value. Now, with the common ion, all right, there is the separation of solubility of an sparingly soluble salts such as calcium iodide. It even become less soluble in H2O when you have a common ion in a solution. Here is the example of silver chloride in a solution of 0.0100 molar chloride ion, which could be from any solution with a chloride ion, such as HCl, in this case, sodium chloride. The mole ratio here is 1:1:1. This is the solubility equilibrium with its KSP value. We account for the chloride from sodium chloride when calculating the molar solubility. And look at how the um, chloride from silver chloride is negligible. The one from the other source is used to find the molar solubility, which is way too less if it was just in pure H2O. You'll use this approach to determine the molar solubility of calcium iodide in part 2. Let's see, using the previous example, if we dissolve lead to bromide in a solution of or rather 0.0500 molar hydrogen bromide, given the KSP value, there is the common ion from the second solution. From Blechatelier's principle, we stress the system is stressed from the product side, which means less amount of lead to ion and bromide ion will be produced from dissolving lead to bromide in H2O. It's just stressing the system by increasing the concentration of bromide ion. Hydrogen ion will not affect anything. It's not part of the solubility equilibrium. This is the solubility equilibrium in H2O. So you proceed by using the same approach as for silver chloride we looked before. This is negligible. The bromide cancelled out here is from lead to bromide. This is the concentration from hydrogen bromide square. And if you plug in, rearrange the equation, solve for lead or concentration for lead, this is the molar solubility of lead to bromide in a solution of 0.0500 molar HPR. Because of the three significant figures, you should run your answer to three significant figures. If you compare with the previous molar solubility of the same compound in H2O, this is less, or the molar solubility is small in common ion compared to in H2O. In today's experiment, you will or you have part A, part B. In part A, uh, you will determine the molar solubility of calcium iodide in pure H2O. There is no calcium added in there. Remember, calcium is used to determine the molar solubility of calcium iodide because of 1:1. Don't forget to read the label. Solution should be for part A. If you know the concentration of each ion in the solution, you can plug in. You can plug in the ion product constant or solubility product constant to get the KSP, and that is the main objective, is to determine the concentration of which ion and then plug in this equation to find the KSP. Uh, Note that if you know the concentration of either one of them, you can find the concentration of the other one. Say that, let's say we know the concentration of calcium, multiplying it by 2, you get the concentration of iodide and you plug in the equation. Or alternatively, you can determine the concentration of iodide divided by 2 to get the concentration of calcium, and you plug in the equation to find the KSP. And that's what we will be doing today, uh, is to determine the molarity of iodide first, and then figure it out the concentration of calcium. We plug it in this equation. How do you find the how do you find the molarity or concentration of redox? It's based on it's based on uh, redox titration, titrating iodide ion with sodium thiosulfate. This is the titran. Titran is 0.0100 molar sodium thiosulfate, and the analyte is the iodide. Of course, you have done titration before. The analyte in this case goes in the LMR flask. The Titan goes in the puree. Take note that here we have 5 ml. Why did I pick 5 ml, or how will you end up with 5 ml? It's not using graduated cylinder, but it's a function of the volumetric pipette provided. It's a function of volumetric pipette. Remember, the meniscus is always or should be at the calibration mark. With this, the titration equation, this is the titration or balance titration equation. Take note of the mole ratio between the iodide, or iodide, sorry, not iodide, iodide ion, and the titran thiosulfate. It is 1 to 6. Now, on the whiteboard, you see initial and final, assuming that you titrate an aliquot of 5 ml of saturated calcium iodide and take 20 ml, 2 places of decimal. Look at the initial. So when you record your volume, it should be to 2 places of decimal. Determine the molar solubility of calcium iodide in pH2, and then follow-up question is, how do you go about determining the KSP, the solubility product constant? This is a 1 to 2 ratio ion from the solubility equilibrium, 1 to 2. Remember, the calcium iodide solid dynamic equilibrium with calcium ion plus iodide ion. This is iodide ion with a mole ratio of 1 to 1 to 2. So first, to determine the molar solubility, we need to find the mole ratio. From the titration, we can find the number of moles of thiosulfate using the molarity equation. Molarity times volume in liters. Volume is determined by subtracting the initial from the final, or rather volume of thiosulfate used is V final minus V initial. This is the number of moles. Always remember to include the units. Don't just write down the number without the units. So these are the moles of thiosulfate, which uh, neutralize or react with the iodide ion in saturated solution of calcium iodide. With this, what I've highlighted here is the mole ratio. 1 to 6 is the mole ratio. So next, let's find the number of moles of iodide. It's 1/6 the moles of thiosulfate. Again, significant figures, three significant figures with the units. From here, we can find the molarity of iodide ion. We can find the molarity of iodide ion. This is the concentration. Remember, the aliquot was 5 ml, three significant figures. Divide that by the number of moles divided by 40 milliliters, and that's the molarity. With this, we can use the mole or the coefficient in the balanced equation here that it is 2 to 1. Therefore, the concentration of calcium is 1/2 the concentration of iodide. 1/2 of this gives us the molarity of calcium, which is basically the molar solubility of calcium iodide in pure H2O. So if we know the concentration of each ion, we can plug in the solubility product equation. The KSP equation is obtained, the KSP equation is given here, which is used to find the solubility product constant. Remember to square the concentration of iodide times the concentration of calcium to get the KSP value. And this is what you will be doing in this experiment. Let's look at the apparatus. May not be all what you need. Please read the procedure. You may need more than what I have on the screen here. Purettes are by the dip sink. You should have a class in the drawers, purette clamp. The balance is by the balance table. This is the volumetric pipettes that are from along with the pipette filler. Let me just direct your attention to step number 5, all right, and 4, or just step 5 and 4. Common mistake students do make is thinking that during the titration, once the solution turns very light yellow, they record it as the final volume. That's not the final volume from the puree reading. Once your solution turns very light yellow, that's the time you need to do what? You need to add 1% starch indicator, which is present on or is given. So on the paint top, 10 to 12 drops of 1% starch should give you a dark blue color. If you don't get a dark blue color, any color is okay. I've seen it work before. At this point, be careful when adding the titrant sodium sulfate. You got to continue with the titration, adding drop by drop at a time until the solution becomes colorless. That is when you got your final volume. Using example here, this is my final volume when the solution becomes colorless. From there, you can now use this equation to determine the volume of sodium thiosulfate required in first titration. So take note of 4 and 5. Where is the P final? Now, as far as the data sheet is concerned for part A, make sure you include names of your lab partner or lab partners if you are working in a group. And uh, don't forget to write the balance titration equation. It's given in the lab manual, as well as the equation for or solubility equilibrium is given here. You are taking notes. This is the solubility equilibrium for calcium or iodide. Now, the rest of the information, this is for trial one, this is for trial two for part A. Let's see, volume of calcium iodide aliquots, just a sample. Remember, this is in liters. It's a function of the volumetric pipette. See the capacity of the volumetric pipette, change that to liters. Of course, from the titration, you will feel the rest. For the moles of thiosulfate, your titrum, it is determined from the molarity, all right, molarity equation and the volume in liters. This is the molarity of thiosulfate and the volume used in titration in liters to get the moles. Then from the titration equation, 1 to 6, you can find the number of moles of uh, iodide present. Moles of iodide present is 1/6 moles of thiosulfate you get from above here. With this, you can now determine the molarity of iodide, volume in liters, and the number of moles from the equation here to get the molarity. And then from the background, you know the moles of, you know the molarity of iodide ion, you can get the concentration of calcium. Remember, molarity of calcium is the molar solubility. This is the molar solubility of saturated calcium iodide for part A. And from here, you can just plug in the KSP equation or solubility product constant. For the two trials, you find the average. At this point, you should be able to uh, write the solubility product equation without plugging in the values here, but we need the numerical, or I need the numerical value here from the last item on the data sheet for part A. Part B is the same. Part B is the same as part A, except this, the saturated calcium iodide is in a solution of calcium ion, calcium nitrate, which is the common ion between common ion here is calcium, which is in calcium iodide, saturated solution of calcium iodide and calcium. Just like in part A, the volume of the aliquot in a function of the pipette, which is 5 ml. You'll do the titration. Please pay attention to step number 5. The rest is the same as part A to get the number of moles of iodide from the moles of thiosulfate. Moles of iodide present is 160 moles of thiosulfate. Then from the molarity, from the number of moles of iodide and the volume in liters, you can calculate the molarity. Now, this is a little bit tricky. Predicting the concentration of iodide with 0.0500 molar calcium ion, please see the background. Note that you must use the KSP from part A. Look at the whiteboard or the screen on the left side here from part A. You should have the numerical value for KSP. Now, with the common ion, the concentration of calcium from calcium nitrate will suppress the concentration of calcium ion from calcium iodide. This is how you set up your equation to find the predicted. Look at the predicted. This is how to go about with determining the predicted concentration of iodide ion. And once you figure it out, the concentration, you just have to use the ratio between calcium ion and iodide ion. And from here, you can find the average solubility. Remember, solubility of calcium iodide is a function or molarity of calcium, which is this value divided by 2 will give you the average. Once you're done, the solution can go down the drain. All right, you can neutralize or just discard down the drain. Except if you have excess HCl, you can neutralize before discarding off down the drain. Remember, PPE, wear safety goggles, close to shoes, lab coat. Before next week, you should be able to complete the pre-lab on predicting precipitation reaction on page 187 and upload the data sheet for solubility and common ion effect. Thank you.